3 says, based on the data from the past 50 years, the world population in billions can be approximated by this function, where x equals 0 is 1950. Estimate the population in 2010. If x equals 0 is 1950, then the year 2010, x will equal what? X equals 0 is 50. 2010 would be x equals... No. X equals 0 is 1950. This is what y'all did that first chapter. 60, thank you. If x equals 0 is the year 1950, x equals 1 would be 1951, x equals 2 is 1952. So the year 2010, you need to know what x is, would be 60. There you go. So what you're actually trying to find there is g of 60. You want to know the population 60 years later. So g of 60, let's find it. To find g of 60, you're going to do 2.5 times 1.0185, is that right? 1.0185, right, to the 60th power. And just type it in your calculator. No problem. Second quit. So 2.5 times 1.0185 raised to the 60th power. Yeah, about 7.51 sounds good. And again, that's population in billions. 7.51 billion people. And again, that goes back to what we were discussing the other day. It's kind of scary about population growth. Because population growth is exponential. People grow exponentially. In what year will the population be 2.5? There's one on your homework like this. Is the only reason I'm working this one. It sounds hard, but it's not. It said, in what year will the population be 2.5 times as big as what it is in the year 2010? Yeah, to find out, okay, this is what it is. Go back to your calculator. That's what it is in 2010. We want to know when will it be times 2.5. 2.5 times bigger than that. So pretty much that question, the easy way of saying it is, when will the population reach this? When will the population reach 18.77 billion people? So the way we find that is we take this and we set it equal to the 18.77. So let's go back. 2.5 times 1.0185 to the x power equals, and don't clear your calculator because we're going to use that, 18.77. Since it is such a big number, so many decimals, I would leave it on my calculator. Go ahead and move 2.5 over, divide by 2.5, and let's clean this up some. So divided by 2.5 gives you 7.51. So this stuff equals 7.51. So we're going to graph this to the x power equals, or minus 7.51 equals 0. And then try to find out where it crosses. So y equals 1.0185 raised to the x power minus, I'm going to throw in a few extra decimal places. Second quit, what was it, 7.50934? Just to make it a little bit more accurate. Graph. And with the same window we had a while ago, we don't get a graph. So let's broaden our window. Let's do 0 to 100. See if we get anything there. So luckily, well, you get part of it. Luckily, 100 years later, you haven't reached that. So let's try 150 maybe. Yeah, I probably should have changed my scale on that one. Let's go back and change the scale. Let's try, well, 10 would just be 15 marks. That won't be bad. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, about 110 years. So to find the actual second calc, yeah, it looks right on it. So left bound's 100, right bound's 120. So 109.98, right at 100. We'll call it 110 years. It doesn't matter. I don't ever even change the guess. I just hit enter again. Yeah. As long as your left bound and right bound's right, the guess won't matter. So it's going to take 110 years for this to grow to however many billion we was talking about before. But again, that's kind of scary. From 2010 to 110 years later, let's see, 2010 to 2120. In that 110-year span, the population grew 2.5 times as big as what it was in 2010. Yes, that's it. That's it. Wait till 2120, which I'm probably not going to be around to see it, but yeah, they're all factored into that. The world population, that's what they're saying, the world population is growing at that rate. So example 4, here you go. Good deal. Example 4 says the amount of 1 kilogram of plutonium that remains, and this gets into the whole carbon dating and all that. The amount from 1 kilogram of plutonium, that's Pu-239, that remains after X years can be approximated with this function. Estimate the amount of plutonium remaining after 1,000 years. So again, all you're doing is finding M of 1,000. So 0.99997. 0.99997 raised to the 1,000 power. 0.97. Most of it's still there. Okay, it started with 1 gram, I believe is what it said, so after 1,000 years it has 0.97 grams left. So 0.03 grams have left it. Let's see. Talk about E now, and hopefully you remember E from Algebra 2. It says there's an irrational number that occurs naturally many times that we discussed when we discuss exponential equations. The number is represented by the letter E, and E is equal to, there's your approximation, similar to pi. E is equal to 2.718281828459045, and so on and so forth. Most scientific or graphing calculators will have a button E to the X, and actually the 83 for some reason has 2 E buttons. I guess it's that important. You've got E here above the division symbol, and you've got E over here above the natural log symbol. This E is when you want to raise E to a power. This makes absolutely no sense to me. This is where you want to raise E to a power. Like if you want to do E to the second power, you could use that E. The one over here, E to the X. This E is just plain old E. But why in the world would you not just do E to the second power like that? I don't know. I would just put this one E button on here, and then if you want to raise it to a power, then you could do raise to the second power. But I don't know. I didn't design the calculator. Remember, when working with a function involving E, it should be treated as a number. So don't let the E throw you off at all. E is a number. E is 2.718, like pi.